you missed points on the one I graded. Let's review why. Does someone have the homework sheet?
Yep. Wait, which one did you grade?
The first one. I thought, oh, let me do an easy one for you guys. I thought, oh my gosh. Okay.
Wait, did you take points away, or was this just like you gave us points out of pity?
You happen to do it right.
Okay.
Wow.
I didn't know if I...
So, yeah, so it says, show that the superposition of two co-propagating cosine waves, i.e., the real representation of two monochromatic scalar plane waves. So they're scalar waves, not electromagnetic, and they are plane waves. So you know what the space and time dependence is. It's just omega t minus k dot r, but they're propagating the same direction, so why not just pick the direction of propagation to be z, just to make it easy? So omega t minus kz. So a lot of you didn't have to do what you did. You know, just start off with the two cosine waves, two scalar plane waves, add them up, and then the question says, to show that those two co-propagating scalar plane waves is itself a scalar plane wave, and that the amplitude depends on the relative phase. So do you have to calculate a radiance? Does it say a radiance anywhere in here? Nope. You're just looking for the total field. So, okay, so just read the questions carefully. It gives you a lot of good information. So, any questions about any of those things? Yeah.
So we have 2 homeworks left that
Yeah.
haven't been done?
Yeah, and the next one, homework 6, is due a week from today. I can't remember if we set that or not. I think we did, but whatever. So a week from today. And then there's just one more. Of course, there's only 3 weeks left, so.
Which day is our final?
I think what we'll do is a take-home final.
Oh,
So last day of class, I'll hand it out, and then we'll make it due someday. I don't know what day yet.
Because the scheduled time is on that first Saturday of finals.
Saturday. Yeah. I mean, I'm happy to be here Saturday. I'm usually here Saturday, but I would rather not have you be under a time limit. So I'd rather that you feel more relaxed and just take whatever time you need. So that's why I'd prefer to do a take-home exam.
And the final will just be like similar to the homework, similar format as the homework,
Should be.
just a bunch of.
That's my hope.
Okay.
Yeah. I mean, I'm not intending for it to be otherwise. You may disagree once you see it, but it's just not. It's not my intention. But there's still some material we haven't covered yet, and I'm going to point out one of the things that we haven't covered yet when we get there that will absolutely be on the final. And you'll have some homework on it for homework 7, so hopefully you'll be up to speed. Okay, any other questions? All right. So, as I recall, we left ourselves in a great state of suspense as to the results of the end-slit interference problem. But probably some of you can't even remember what we were doing. So let's just kind of refresh our memories. So we said that we'd start with a plane wave. So it's just propagating. And it's instant on a screen where the screen has some slits in it. And the slit separation is D. And then light that goes through the slit is going to diffract and come out as kind of a cylindrical wave. And we said, let's just look at the ray from each slit that goes in a particular direction, gather it together with a lens, and use that lens to focus that light down to a particular point, at a location X on the X-axis. And we wanted to know what's the interference here at that position X. And we recognize that everything from here to point X will have the same path length. So it's only these little path lengths that matter in terms of giving a relative phase to each of the, or to light from each of the slits. And then we said, let's write down the fields, recognizing that if this is the angle theta, and so that's theta, then we have that, and then this is the back focal length of the lens, and theta is about x over f. So in other words, we're in the paraxial regime. And so when we talked about what model to use, we said, well, of course, let's use the scalar model, because this has some polarization state. We don't expect it to change going through here. So same polarization state, it's paraxial, so perfect. Let's use the scalar model. So then all we had to do is write down the complex amplitude of the field at x for light traveling each of these paths. And we noted that the complex amplitude at a given point is just some complex number, which means it has an amplitude, it has a phase. So we said for light going through slit 1, it'll have some amplitude, call it A. It'll have some phase, call it gamma. And then we said light going through slit 2 will have some amplitude because the paths are nearly the same. We said let's let the amplitude be the same. And then it will have some phase, and it will be the same phase as this plus whatever phase it picks up by traveling that distance minus or delta s. So that would be e to the minus j 2 pi over lambda naught n delta s. And then we said delta s has a particular functional form, and we looked at what that was. Do you remember what it was?
D times x over f.
Yeah, so we'll call it xd over f. So that's the functional form. And this thing, we said let's just call it delta phi. So U3 then is A e to the j gamma e to the minus j 2 delta phi, and U4 A e to the j gamma e to the minus j 3 delta phi. So those are, almost had a sneeze. Those are our expressions then for the there it is, for the four fields. So the complex amplitude for the total field is just going to be the sum of the individual complex amplitudes. And looking at this, we can see that we have A e to the j gamma in common. So we're left with the sum I equals 1 to 4 in this case, e to the minus j I minus 1 times delta phi. And then we can change the sum a little bit just to make it more convenient. A e to the j gamma sum m equals 0 to 3 in this case, and let's just call it n minus 1, just generalizing. So this would be n and n. Then we have e to the minus j m delta phi. And so that's the complex amplitude of the total field at that point x. And now the good thing is that this sum can be summed analytically. So if we do that, we have basically the sum m equals 0 to n minus 1 of alpha raised to the nth power. And we can sum that, and it's 1 minus alpha raised to the nth power over 1 minus alpha. So that's the analytical expression. And if we substitute in for what alpha is, which is just e to the minus j delta phi, then we can write that as e to the minus n minus 1 delta phi over 2 times sine of n delta phi over 2 over sine delta phi over 2.
What are we solving for here?
So we're just looking at this sum, and it has this functional form with alpha equal to e to the minus j delta phi.
Gotcha, okay.
And so we're recognizing that, oh, we can sum it. It has an analytical expression. So that
So those
means,
signs are not in the exponent, right? They're just multiplied by that e, or are they?
oh,
Okay, gotcha.
yeah, thank you. So that means that the total complex amplitude, then we can write as a e to the j gamma, and then we have minus n minus 1 delta phi over 2, and then we have sine of n delta phi over 2 over sine delta phi over 2. And you notice that this complex exponential out in front is just an overall phase factor. So it really doesn't matter. And in fact, when we take the irradiance, when we calculate the irradiance, which is just magnitude squared of that total complex amplitude, then of course it goes away. And we're left with a squared times sine squared n delta phi over 2 over sine squared delta phi over 2. And so that's our irradiance, and delta phi, recall, is 2 pi over lambda naught times n x d over the focal length. So we've gotten the irradiance in the plane of observation here along the x-axis. And now we just need to understand, what does that mean? So any questions? Yeah.
What is delta in those, in the U1, A to the EJ, J delta? What are those deltas?
The
Oh,
delta
that's just
phi?
the general phase, right? Just like the initial.
Oh,
phase.
you mean the gammas here?
Oh, gammas, yeah.
Yeah, it's just whatever the phase is for this light coming in here,
Yeah.
plus whatever the phase it picks up and traveling over there.
Okay.
Yeah. Yeah.
I still don't see the jump from the summation to that e to the negative n minus 1.
This one right here?
Yeah.
Oh, I skipped a bunch of steps. So basically, I plugged in for alpha and did a bunch of rearranging.
So that 1 minus kind of works itself into that, and then
Yeah, so basically, here, what you end up with is, 1 minus e to the minus j n delta phi over 1 minus e to the minus j delta phi. And then you can pull out and e to the minus j n over 2 delta phi from the top, leaving you with e to the j n over 2 delta phi minus e to the minus, no, that's a plus, then from the bottom, e to the minus j delta phi over 2, and then this is e to the plus j delta phi over 2 minus e to the minus j delta phi over 2.
Right, and then those turn into signs.
Yeah, and then these turn into signs, and then we're left with this, which is where that thing comes from. Yeah. Yeah, so just some algebra tree. Okay. So, we've got this irradiance, and it's kind of funny looking. Notice what happens when delta phi goes to 0. And we've got sine of 0 over sine of 0, which is 0 over 0. And that doesn't sound too great. L'Hopital's rule. So, in this case, the irradiance becomes a squared m squared by L'Hopital's rule. And you can look that up, it's not a big deal. Okay, so when the phase differences go to 0, then I should have constructive interference. And we saw when we talked about constructive interference for multiple beam interference that you end up with n squared times the irradiance of a single beam. And a squared is the irradiance of a single beam, single one of these guys. So that does work out. So if we look specifically at the case n equals 4 and plot as a function of delta phi what the irradiance does, then basically at delta phi equals 0, we should be here at n squared a squared. And then when we get over here to 2 pi, in fact, let's go this way too, to minus 2 pi. When we get to 2 pi, then we've got sine of n times pi and sine of pi. Well, we're back to the denominator and numerator both being 0. And end up with, again, this is n squared a squared. Likewise over here, n squared a squared. So evidently, whenever delta phi is an integer multiple of 2 pi, then we have a maximum in the interference. And then what it looks like in between is something like this for n equals 4, etc. So basically, there are n minus 2 side lobes between the main lobes. There are n minus 1 nulls between the main lobes. And then the main lobes have this irradiance that's n squared times the irradiance of a single beam. Okay, so if we looked here in this screen, then this is the pattern we would see. And it turns out that there are a number of instances in optics where you end up with interference of this form, where you have a bunch of beams that have this form in terms of the phase difference. In fact, in my graduate work, one of the things that I did was these stratified volume holograms that I won't go into, but it turns out, and I didn't recognize this, But it turns out it has exactly this type of interference behavior in terms of what the functional relationship looks like on the change in phase. And so you end up getting this analytical expression out of that situation. Okay, any questions? Yeah, Carlos.
So does it look like the same way in the y-axis? Do we get a similar gradient?
So I didn't really say anything about that, but my unstated assumption is, this is a slit, so this is basically a one-dimensional problem. So this lens is really a cylindrical lens, and so this plane is the same no matter where we come along the z-axis. So that's the same. Yeah.
Are these side lobes, are they all the same height, or, okay? And is there like a specific value they take, or
Well, for the n equals 4 case, they're the same height.
does it depend on what your n is?
Yes.
Okay.
Yeah. Yeah. Okay. Yeah.
So how do you get that n squared? I get the a squared part.
Here,
But, yeah, and then in your max value, where does
it's
the n squared
it's
come from?
as sine squared n delta phi over 2 over sine squared delta phi over 2. As delta phi goes to 0, this goes to n quantity squared.
Oh, yeah, yeah, because it's 0, 0.
Yeah. Which is a L'Hopital rule thing. You can analyze it with L'Hopital's rule. Which basically just means expand the signs in terms of their series expansion, drop the higher order terms, just keep the first order term, which is valid when this is getting small, and then that just falls right out. Okay. All right, so now what we get to do is another example. So this is an example of division of wavefront to generate a bunch of beams. And now we need to do division of amplitude to generate a bunch of beams and see how it works out. So you ready for me to erase it? Okay. All right, so we're going to go back to the dielectric slab. And let's draw it this way. Let's say our slab is here and has height d, refractive index n2, immersed in a medium of refractive index n1. And let's consider a single ray that comes in here at some angle theta 1. Then we'll get a first surface reflection at an angle theta 1, and the rest of the light will transmit on through, and then we'll get a second surface reflection here, generating a ray. We'll get some transmitted light, and then in general, some of this will reflect, create some transmitted light, reflect again, transmitted light, and et cetera, et cetera, et cetera. So we generate a whole bunch of parallel reflected and transmitted rays. So we take a lens to bring those all into focus in the back focal plane of the lens for the reflected light, and similarly for the transmitted light, to bring all of those together so that they can interfere on an observation screen. Okay, so that's our basic setup. And in both cases here, we're looking in the back focal plane of the lens, bring those parallel rays together. So the lens is acting as an angle to position converter. And what we want to know is, for the reflected light, what is the irradiance here? For the transmitted light, what is the irradiance there? So that's our objective. Now, we need to just refresh our memory on some notation that we developed, and that is the reflection coefficient when we're in medium 1 going towards medium 2, we called R12, and the transmission coefficient when we're in medium 1 going into medium 2, we called T12. And likewise, reflection coefficient when we're in medium 2 going to medium 1 is R21. And for the transmission, it's T21. So remember, that's our notation. And these are either S or T, reflection coefficients and transmission coefficients, depending upon whether we have TE or TM light. So here we have an instant field, and if we want to write down that field, what would be the complex amplitude vector for the instant field?
As a polarization, amplitude, phase.
So it has polarization, call it P hat. Amplitude, call it E naught.
And
Phase.
the J phi.
What's that?
J phi.
J phi, okay.
And
We're going to use phi again, so, okay, let's use phi, and we'll use something else later.
and e to the minus j k dot r.
K dot R, yep. Where K is there. Yeah, perfect. So it has a polarization state. We just make it a unit vector for the polarization state. Amplitude, phase, spatially dependent phase. Usual thing for a plane wave. Yeah.
Maybe we spoke about this already. Is there a reason why division of, what is this one, division of amplitude?
Uh-huh.
We're gonna use the electric magnetic field instead of?
Yes, I wanted to bring that up. So thanks for asking that. Yeah, when we look at this problem, do we want to use the scalar model or the electromagnetic model?
Electromagnetic,
And why?
because it's polarization.
Yeah, because it's reflection and refraction, so, and that's polarization dependent. So we have to use the electromagnetic model. Okay, having said that, here, the polarization state could be anything, right? But for us to use for no reflection and transmission coefficients, we need to either have TE or TM, or take this and decompose it into TE and TM components. So in order to make our lives easy, let's say that we have either TE or TM polarization. We don't need to specify which, because in the end, specifying which one just means which reflection or transmission coefficient we use, TE polarization, T or S, or rather TM, depending upon which one we start off with. Okay, so with the polarization state specified as being one of these two things, then the E to the J phi, do we care about it?
No,
And why?
because it doesn't matter which part of wave you start.
Yeah, once we go to calculate the irradiance, any overall phase factor will always, or common phase factor always goes away. So that E to J phi is not going to matter. Amplitude, yeah, that matters. Spatially dependent phase, will that matter?
Yes.
And how will it matter?
Because each of those different rays is going to travel differently.
Yes.
Pick up some more phase.
Exactly right. Okay, so let's say that, let me switch colors so it's, doesn't get too messy here. Let's say that right here, for the instant wave, let's just call the phase there 0, just so we can get rid of it now. Then the field, the only piece of it that we care about is E0. Okay? Then the reflected phase, or rather the reflected field, or complex amplitude of the field, what will it be?
Oh,
E0 R. Yeah.
So this one will be R12E0. Okay? And then we have the rest of the field that gets transmitted through, and then that gets transmitted through this interface. So what will be the amplitude and phase of the field here?
T21,
One, two,
T21, T12,
Yeah.
E naught, and then the phase will be however much phase we pick up and going from there to there. And it turns out that's going to be common to all of these, right?
Yeah, yeah.
So it doesn't matter, so we can just throw it away right now. Okay?
Wait, why is it gonna be common to?
Was the same.
Because this one came from this path, so that's common. And this one over here, came from that path. Again, this is common. So they're all going to have the phase associated with propagating that little leg. So it's going to go away. So we don't even need to track it. Okay, so then we have light reflected up to here. And so what's going to be the amplitude and phase of the beam that comes out here?
T21, R21,
T21.
Oh, sorry, T12. Yeah.
No,
Okay, either way, whatever. T12,
R21.
R21, T21, E naught, and then phase. Remember what the relative phase for the two-beam version of this was between that and that?
T2D.
So we called it delta phi 4 pi over lambda naught n2 d cosine theta 2. Theta 2 is the refraction angle here. Okay, and now let's give this a different symbol because the delta phi is going to get clunky real fast. Let's call this delta. So that's the phase difference between adjacent rays. So this would be e to the minus j delta. So that's its relative phase to the first ray. And we derived that already. Okay, so let's go now with the light that gets reflected from that interface down here and then that gets transmitted. So here, I'm going to pull it out to the side. What will be the amplitude and phase of light coming out in that ray?
T21, T12, T21, T12.
So let's start from here.
Or no, it's the reflection side.
T12, and then here we get
Reflection.
R21, and here we get
R21.
R21, another R21, and here we get T21, E0, and then how much phase? This relative to that? E minus j delta. Okay. Now let's go to this one. I'm going to pull it out to the side. So what do we get for that one, for amplitude? we have T12, R21, 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 so R21 cubed, and then T21, E0, e to the minus J2 delta. Okay? And we could go on, et cetera, et cetera, et cetera. We can just follow it all through. And once we do that, then we can write down the reflected field. It's really the complex amplitude of the reflected field, R, as just being the sum of these things, right? So let me gather terms. So the E0 is going to be common, so I'm going to pull that out. And I have an R12 for this first term right here. And then notice all of these terms. Notice they have a common T12, T21, R21, e to the minus j delta. And then from here, that'll be a 1 plus, for the next one, what'll it be?
R21 squared.
R21 squared. And
The next one will be R21 to the 4.
yeah, but this one, we're still on this guy.
E raised to the power negative j delta.
E to the minus j delta. We have that term. And then the next one is going to be R21 squared,
This all terms
e to the minus j delta squared plus, etc. Right? And we could similarly write down for the transmitted beam. I'm not going to bother. Okay. Now, as long as this is less than 1, and yeah, it should be less than 1, right? R21 squared? It's got to be less than 1. Otherwise, we'd never get any light to go in. So it's less than 1. If we have that and the number of terms goes to infinity, then that can be summed analytically, which is very convenient. And so we end up with E0, R12, and then we have plus T12, T21, R21, e to the minus j delta over 1 minus R21 squared e to the minus j delta. Well, that's highly convenient. And now we can make use of the fact that R21 is minus R12, right? We've been through that before. Okay. And then we probably haven't been through this before, but T12, T21, if you plug in and rearrange terms, what you find is that it's 1 minus R12 squared. So if we plug those two back in here, we end up with E0, and then we have an R12, 1 minus e to the minus j delta over 1 minus R12 squared e to the minus j delta. So I skipped all the algebra. And notice the ratio of ER to E0 is just this thing, the square bracket, so R12, 1 minus e to the minus j delta over 1 minus R12 squared e to the minus j delta. And ER over E naught, what's that? This is still fields.
Okay, so it's,
That's our,
Isn't it the total reflected field divided by the incident field? And this total reflected field takes into account all of the multiple reflections, all of the phase shifts. So we could say, why don't we just call this the reflection coefficient starting in medium 1, having a slab of medium 2, and coming back out on the other side in medium 1. Let's call it R121. So this is
oh, and that's
basically
true for, and that takes into account every reflection.
every reflection.
So
And-
we are considering, after successive reflection, it will somehow end up transmitting into medium 1 again?
No, no, but this is the physical situation where we start in medium 1, have a slab of medium 2, and the other side we have a medium 1 again. And that medium 1 is important because that reflection coefficient is R21, which is minus R12. If this was a different medium, say N3, then
Those two will be
this
again.
wouldn't be true.
Yeah.
And of course, that's a situation we're going to do later. Okay, any questions? We're good? Everyone follows what we did? Got the logic of it? Okay, so we could do the same thing for the transmitted, and I'm not going to do the steps. I'm just going to write down the result. And have this total transmitted field divided by the incident field, and it's equal to T12, T21, e to the minus j, delta over 2, divided by 1 minus R12 squared, e to the minus j delta, and we can call that T121, the field transmission coefficient of the system. It takes into account all of the multiply transmitted beams, the relative phases, everything. It's all embodied in that. Okay, so now what we can do is we can calculate the irradiance, and so the irradiance for the reflected light is going to be 1 over 2 times eta magnitude squared of this amplitude ER, which clearly is in general complex. And if we plug in and do some algebra, and again, I'm just going to skip the algebra because you're capable of doing it, what we end up with is I naught, which of course is the square of this guy, divided by 2 times eta, times something f, I'll define in a moment, times sine squared delta over 2 over 1 plus f sine squared delta over 2. And the transmitted beam is 1 over 2 times eta, the transmitted magnitude squared, which is I naught, and then it's equal to, or then it's multiplied by 1 over 1 plus f sine squared delta over 2. And this f is equal to 2 times R12 squared over 1 minus R12 squared, quantity squared. And R12 squared, what is that? The Fresnel reflection coefficient squared is what? Do you recall? Remember, reflectance
that's the trend.
is magnitude squared of the reflection coefficient?
Reflectance?
Or if the reflection coefficient is real, then it's just R squared. So this would be 4 times the square of the reflectance over 1 minus the reflectance quantity squared. And we call this thing the coefficient of finesse. So it has a name. And note the name is not the finesse, it's the coefficient of the finesse. Okay. Now notice that if I take the reflected irradiance and the transmitted irradiance, what do I get?
We should get your incident, right? Hopefully.
Hopefully. So if you take this and add it to that, what do you get?
I know.
Yeah.
Yeah, because this term plus that term is just 1, right?
Yeah.
So that's I naught, so good. We've got energy conservation, which is good because I said this is a dielectric slab, meaning it's lossless, so there's no loss mechanisms here. Okay, now if we take a look at the transmitted irradiance, and we ask, when is the transmitted radiance a maximum? Under what conditions do we get that to be a maximum?
That sine squared delta be as small as possible.
Delta
Yeah.
0.
When that goes to 0.
Yep.
So we end up with 1 over 1 plus the coefficient of finesse for the case of delta equals to 2 pi times an integer, which is when the sine squared is 0. Okay, and in that case, the reflectance will have to be, or the reflected power has to be a minimum then, right? And you look at this and you say, oh, well, yeah, it's a minimum, it's 0. So think about that. We've got a slab, we've got a plane wave instant, and under this condition, what happens?
Everything is transmitted.
Yeah, oh,
Why you
I
like
screwed
that?
up. I screwed up. Sorry. It's 1, that's just I naught. There we go. That's a much better story. Okay. Okay, so we've got a slab here, like a piece of glass or something. And what are we saying happens? It's like it's not there. Because all the light's transmitted. None of it is reflected. That's kind of weird. And that actually foreshadows anti-reflection coatings, which is going to be the same situation, except we just have a different material here, but we designed this so all the light transmits. So it's like there is not an interface or a set of interfaces. Okay, so that's kind of a weird one. Why does it happen? What must be going on here?
Oh, destructive, fully destructive.
Completely destructive interference.
So it's more spooky action.
Yeah. So basically, all of the amplitudes here with the relative phases are just right, so they completely cancel out.
And then the light has to put the energy on.
That's right. That's right. And likewise, these all fully constructively interfere. Yeah. So, okay. Now let's look at the opposite situation. when the transmitted light is a minimum, how much light is transmitted? So when IT is a minimum, that means the sine squared has to be a maximum, right? In which case it's 1.
-1
Fine.
And that's when delta is equal to 2m plus 1 times pi. And in that case, the reflected light is a maximum. And what's it equal to?
One minus that,
Yeah.
times I don't know.
Yeah, so going here, the sine squared is 1, so it's I naught f over 1 plus f. Okay, so what's that telling us?
Can't make it into an awesome meter.
That's right. We can never get this thing to reflect all of the light. So if we just have a dielectric slab, you can't get all the light to reflect. You're always going to have some light transfer. So if you're looking out the window, you can never have it become a perfect mirror. There's no set of conditions that will allow it. Okay. So now let's define a few other things. I'm going to define it right here because I need that board space. There's something called the Airy function. Have you heard of an Airy function before? Okay, turns out there are a couple of them in optics, and so this is probably not the one you've heard of if you have heard of one before. So the Airy function, we'll give it a script A, is 1 over 1 plus f sine squared delta over 2. And hey, that's just this thing right here. So evidently, the transmitted irradiance divided by the incident irradiance is just the Airy function. And then there's the complementary Airy function, which is 1 minus the Airy function, and that's f over 1 plus f sine squared of delta over 2. And evidently, that's the reflected irradiance divided by the incident irradiance. Okay, so what we want to do now is get a feel for what these things mean, which is the same thing as saying reflected and transmitted irradiance. What does it look like? And so let's plot as a function of delta what the transmitted irradiance divided by the incident irradiance looks like. And if we go 0, 2 pi, 4 pi, and then let's say this is 1, and so we have some dashed lines here just to guide the drawing. Then if we start off with the case of, let's say, r is equal to 0.2, so that means that r squared is 0.04, and we draw what the transmitted irradiance looks like as a function of delta, then basically it goes like this. Something like that. It just looks sinusoidal.
That's the curve for that given R, is what you're saying?
Yes.
Okay.
Yeah, which leads to a coefficient of finesse. We can write down what the coefficient of finesse is. it's equal to 0.2. And then if we increase the coefficient of finesse, meaning we increase the reflectance of a surface, then what happens is this starts to do this. So this is for an R squared of 0.18. And then as we increase it further, what happens is this comes down like this. So that's for an R squared of 0.8. So that's 80% of the light being reflected at each interface here. So it's a pretty good mirror by then.
So this is when you say R squared, you're talking R12 or R21?
It doesn't matter, either one, because of this.
Oh, okay.
Yeah. And so if we draw the corresponding reflection, reflected irradiance, normalized, then, and we say that's 1, and 2 pi, 4 pi, then we get something that looks like this, or R squared equal to 0.04, and something that looks like this, or R squared equal to 0.18, and then something that looks like this, or R squared equal to 0.8. So, if you look at these things, the R squared equal to 0.04 curve here turns out is pretty sinusoidal. But as we increase R squared, it becomes anything but sinusoidal. It's still periodic in delta, but it's not sinusoidal. And if you look at the transmitted light, it becomes very peaky. So the transmission only happens in a very narrow range for relative phase shift. So this actually brings us to an important distinction between two-beam interference and multiple beam interference. Two-beam interference always looks sinusoidal in the phase difference. Multiple beam interference always looks really peaky, having narrow, sharp peaks as a function of the relative phase difference. Okay, any questions?
Yeah, would they, this is a very interesting property that looks like could be used for something, but I don't know what it can be used for.
We're just about to dive into what it can be.
Okay.
Yeah. Jace?
Is the lower graph supposed to be IR over IT? Or
Oh,
is it
sorry,
IR over
I0. Thank you very much. Yep, I0. Okay, so now I need the space over here, so I need to erase it. Okay, it turns out that the analysis we just did for a slab is leads us to a class of interference devices that are extraordinarily useful and are just ubiquitous. They get used all over the place. And that is a Fabry-Perot. Fabry-Perot cavity, Fabry-Perot interferometer, there are different names. But basically, a Fabry-Perot is just a pair of parallel reflecting surfaces separated by some distance d, filled with some refractive index, whatever it is. Could be air, could be anything. So a Fabry-Perot is always that. Now, if D can be varied, then properly speaking, we call this a Fabry-Perot interferometer. On the other hand, if D is fixed, then properly we call it an etalon. But it turns out that people are really sloppy with names, and so,
Etalon?
yeah. So this convention is not followed very well in the literature. But just be aware, if you do hear the word etalon, in your mind you should just translate it to, oh, Fabry-Perot, where the mirror separation is fixed. Whereas if someone says Fabry-Perot, you have no idea. You know, just you have two parallel reflective surfaces, but you don't know if they're fixed or if they move, because people are just so sloppy in using those names. Okay, so let's say that we have a Fabry-Perot here. These are our two reflective surfaces. And let's say that they're, say, really thin aluminum on two pieces of glass. So this is our reflective surface on each piece of glass. Okay, then I could put some lenses here. And I could start off with an extended monochromatic source and have this be one focal length away from the first lens, and then look in the back focal plane of the second lens. And the first thing is, what if I didn't have this Fabry-Perot here? What would I get in the image plane, or get in that plane rather?
Whatever your source was, yeah.
You'd get an image of the source.
So a two-lens system, is this like a microscope or
Yeah,
a
it's like a
telescope?
Yeah, so this is one focal distance away. So this thing gets collimated by the first lens, right? And then collimated light gets focused down to the focal point, the second lens. So this point is imaged to that point. If I start at some other point, I just get collimated light at a different angle, and that gets focused to the conjugate point. Okay, so if I don't have this here, I just get this uniform source imaged over here, right? Okay, so then I pop the Fabry-Perot in there, and what happens?
Well, so very similar to what we did with dielectric slab.
Yeah, this is basically the Hayden fringe setup.
Yeah.
So that's our axis. Well, let's think about it. Let's say we start off with a point here. So we get this situation. We get collimated light there along the axis. What's delta going to be? Because this is a Fabry-Perot, right? It's this thing over here.
question one more time?
What's delta going to be? For the light coming in here parallel to the axis,
Well, it's gonna be zero.
We'll
It's
call that
all
zero.
yeah, delta's gonna be zero. So what's the transmitted irradiance when delta is zero?
It's all of it.
All of it. So in other words, light from this point is going to get imaged here with no perturbation by the fact I have the Bragg throw there. So now what if I just come off a little bit, say up, away from that point? What happens?
And you start getting all the, you do a little delta.
Yeah, then I'm coming in, I mean, light expands, gets collimated, but it's collimated a little bit of an angle, right? So what does that mean in terms of delta?
There's a path difference.
So we're looking at the transmitted case, delta is starting to increase. So I'm going to fall off of this peak here, this transmission peak, till I get over here, right? And as I keep going further away from the axis, what happens?
You're gonna get to 2 delta.
Eventually, I'm going to get over here. And so
So you get your fringe kind of.
I'll get another peak there. And then I keep going, I'll get another peak there. So if I look at this thing just head on, I basically get some light here, imaged from the on-axis position. Then I get some light here, corresponding to delta equals 2 pi. Then I get some light here, corresponding to delta equals 4 pi, 6 pi, etc. Make sense? And then how wide are these interference fringes?
Like how wide is the fringe itself, or like the spacing?
The fringe itself. Yeah, depends on R squared. If R, well, so it's basically going to be this
Yeah.
for whatever R squared I have. And if R squared is 0.18, well, you know, I'm not going to really have distinct fringes. I'm going to have light everywhere with brighter light given by this curve. But if R is decently large, then I'm going to have very little light everywhere except in the fringes, and the fringe width will be determined by R squared.
So if R squared is a delta, or it's 1, is that a delta?
Well, if R squared's 1, then I have a perfect mirror for each surface, and I'll just get all the light reflected at the first surface. It'll never make it into the diagram. Okay, so this then is what we see in the image plane. And notice, all it's done is taken this source and essentially filtered it. For point sources in the right location, they just go right on through, unattenuated. Point sources not in those locations, meaning not, you know, in here, but over here, most of the light doesn't make it through. So in that sense, it's a filter. Okay, so at this point, what we want to do is if I were to start here and just go in some radial direction and plot it, then basically IT over I naught, I'd get something that looks like this. And let's say this is delta equal to 2 pi m, and this is delta equal to 2 pi m plus 1. And so this is the delta axis. Then this is the full width half max of peak. And it turns out that the full width half max in units of delta, meaning in units of phase shift, you can easily calculate it. It's 4 times the arc sine of 1 over the square root of the coefficient of finesse. And because the coefficient of finesse tends to be large, we can approximate this as 4 over the square root of the coefficient of finesse. Okay, so that's what the full width half max is. Then the separation here between fringes is just 2 pi, right? In units of delta. And so we can define something called the finesse, and we'll write it as a script f. And the finesse is the separation between the peaks. So separation between peaks divided by the peak width. And notice that's 2 pi is the separation between the peaks. Peak width is 4 divided by square root of the coefficient of finesse. And so this is square root of the coefficient of finesse times pi over 2. So that is the finesse of this fabric row. And remember the meaning of finesse, it's the separation of the peaks divided by the peak width. That's super important. But we don't have time to get into it, so we'll have to save that for
Conceptually, that's like how well it defines it away. Right? Okay.
yes.
Or how well, I guess it confines it in those areas.
Yeah, we're going to relate it to resolving power next time.
Okay.
Okay, well,